Good afternoon, class. This is MO 869, Introduction to Autonomous Vehicles. Lecture 17, Trajectory Planning Methods, Part 1. Last lecture, we covered up to representation. So we started the robot path planning or trajectory planning section. And in fact, this section is actually contains a lot of content, lecture materials. So last lecture, if you look at the outline of the last lecture, this was simply lumped into path planning, trajectory planning methods. And if I list out all the contents, then there are many contents. And I will have 2 lectures on this topic. And this is going to be part 1 of those 2 lectures. Today, I will cover up to here. And then part 2 will cover the rest of the section. And then there will be last lecture for this module, as well as for the entire coursework. I'm sorry, I take that back. There will be another lecture on recent work and state of the arts in the motion planning research. Okay, so we have 4 lectures to go. Okay, right, overview. By the way, let me go over these sections. So there are 4 sections. Consist of graph-based methods, sampling-based methods, potential field methods, and then some collision avoidance algorithms will be introduced. These are 4 traditional, well-studied path and trajectory planning methods for robots. So we are going to cover robot path trajectory planning methods first, and then we will move on to trajectory planning for autonomous vehicle, how some of these principles are applied to autonomous vehicles. Okay. Motion planning competence. In a nutshell, work out how the robot could feasibly move from one position to another. Simplifying assumptions are our representation of the robot and the world is sufficiently expressive. We know where we are and where we want to go. We have a motion model for our robots, typically cast as an optimization problem, such as minimizing cost, time, distance, energy within the constraints. Path planning problem is as follows. Assume we have a workspace, obstacle region, and configuration space is available with definitions of C-free and C-ops, which is free configuration space and obstacle or occupied C-space. Given a query with initial configuration and desired goal configuration, so origin and destination. And our task is to find or compute a path in the time domain from origin 0 to 1, where 1 being the terminal time within the free configuration space, such that tau 0 is the initial configuration and tau 1 equals to goal configuration. Okay. Approaches and guarantees. There are three main approaches, methods when it comes to path trajectory planning for robots, and those are listed here, and we are going to cover these three methods. Today we're going to cover graph planning, which is a deterministic method, and then next lecture will cover sampling-based planning, which is probabilistic approach, and then we'll cover potential field methods. And these methods use the configuration space abstraction, so requires a preliminary computation of C-free and C-ops, so free configuration space and obstacle space. Some definitions are listed here. So when we say there is guarantees when it comes to planning problems or methods. If we say complete, then if a solution exists, it finds one. Otherwise, returns failure. Semi-complete means if a solution exists, the method finds one. Otherwise, may run forever. Resolution complete is if a solution exists, it finds one. Otherwise, it terminates and reports that no solution within a specified resolution exists. And then there's a probabilistically complete. If a solution exists, the probability that it will be found tends to be 1 as the number of iterations tends to approaches infinity. Okay. Some definitions are introduced. So overview of those three methods are described here. Graph methods is exact and complete. Underlying principle is it requires a priori computation of C space and generation of a roadmap. Then use a discrete graph search method on the roadmap. Sampling-based methods are approximate and not complete, but can be resolution complete or probabilistically complete. Underlying principle is avoid explicit construction of roadmaps in configuration space. Instead, sample a path segment and check for collisions for path and trajectory planning problems. Potential field methods approximate and not complete, suffer from local minima. Underlying principle is integrate over a vector field to obtain a trajectory. Can also be done in reactive mode. Motion planar hierarchy. So this is just another drawing, another figure showing hierarchy of motion planar. We sort of looked at a similar figure in the last lecture, but this gives you different aspects of the motion planner hierarchy. So at high level, we have strategic planning algorithm, such as route planner, which runs quite slow, does not have to run fast. And then there's a tactical layer, which determines short-range route planner. And then there's a reactive planning algorithm, usually takes care of the safety and collision avoidance problems, and works with a controller. Okay. So this is how things are organized to solve a complex problem into by decoupling problems and creating this hierarchy, we can more efficiently solve the problem. Okay. And this is another way of looking at trajectory planning workflow. First, compute a path, and then we smooth the path, and then design a trajectory, meaning we want to create the velocity or position as a function of time, and then design a controller that makes sure planned trajectory is kept tracked. Okay. Let's talk about graph-based methods, which was the first topic. We need to first compute configuration space, where is obstacles and where is this free space, and then generate a roadmap in free space. There are methods like visibility graphs, Voronoi cells, occupancy grid maps. There are many different ways of generating a roadmap. Compute minimum cost path from initial to goal configuration. This is the graph search algorithm that you have to employ to find the solution, and you get the resulting path and trajectory. We have to, when it comes to solving these problems and implementing these algorithms, we have to eventually work in the discrete domain. Continuous representations have nice mathematical properties when we work with math, but it's not always convenient. And when it comes to deploying these algorithms and implementing these algorithms on computer, we need to discretize things and solve numerically. So it is very common to convert a planning problem to some kind of discrete graph representation, then use one of existing search algorithms to solve the optimization problem. There are different representations. There are structured representations versus unstructured representations. Structured ones are include occupancy grids, distance fields. Unstructured ones include exact unstructured representation. There are meshes, and interestingly, graph falls in somewhere between structured and unstructured, because in some sense, graph consists, I will talk more about this, but graph consists of node and edges. So it can be a structured representation, but at the same time, it can cover unstructured environment, and the graph, the shape of graph, doesn't necessarily stick to the physical world or physical representations. So it's quite unstructured. There is a freedom there. So let's start with terminologies. We have vertex and edge, V and E, and graph. G consists of vertices and edges, and we have path that path P will be a subset of this edge set, and then node is going to be described by B and P. There's a directed graph and then weighted graph. If edges contain direction information, if edges have cost value, then different graphs can be constructed. Graph constructions have different types: grid cell decomposition, Voronoi visibility graph, state lattice, lane model, spatial temporal graphs. So there are different types of graphs, and one representation or one type of graph may be suitable for different robot systems. Okay, so please start thinking about what representation would be suitable for road infrastructure. Discrete state-space representation. Let's start with a simple example. We need to reduce continuous state space to a finite set of discrete states. Let's say that set is X, and then we also need to define action space, define feasible actions from each state. That is A of X. And then there will be a transition function. So for given X and A, there will be resulting state X prime. Okay. We can create these grid on a 2D space, and we can make this. We can make this into a graph structure. Let's consider states as vertices and transitions as directed edges. Now we have a graph. Starting node would be XS, a goal node would be XG, cost function C. Now the problem is going to find the shortest path from start to goal using a graph search algorithm. So this is very simple way to represent 2D space and discretize and create a graph, but there are issues with this grid-based representation. For instance, this can limit the type of output path. So we only have you know, if the action space was moving to a neighboring state, then we can only have this type of resulting path. Suffer from poor scaling in higher dimensions. So if the space and the map becomes large, then it's not very scalable. And it can be difficult to select a grid resolution to compromise between being sufficiently fine to retain valid solutions and sufficiently coarse to find a solution in a reasonable time. So if we make this very small, the resolution small, high resolution, then it'll be accurate, and there will be solution will exist. But then it'll take long time, computationally heavy. So, but if we use, very coarse grid or low resolution, then it's going to be a simpler problem, smaller problem, and faster to solve. But the solution may not be very realistic, or may not even exist. For instance, if grid was this big, there is always obstacle in all of these grids, okay? Connectivity between defined by the grid shape can be limiting, especially challenging in higher dimensional spaces. Grids suffer badly from the curse of dimensionality. For instance, number of nodes in a 2D grid, 100 by 100, will give you 10,000, right? And if we assume cells have, if we assume a robot can move to neighboring cell, then we have 4 actions. If we assume we can move to a diagonal cell, then it gives you 8 action choices. And number of, if we apply this in 3D space, then 3D grid will result in what, 100, it's a million, right? 1 million cells, and which has 6 direct phase neighbors. And if we consider diagonal transitions, that's going to introduce 26 action space. If the dimension increases, 4, 5, 60, then the space exponentially grows, and computing and searching for the solution becomes intractable. So let's look at other representations. There's a grid lattice, or state lattice. Create a set of feasible motion primitives and construct a tree that chains the motions into a sequence or a plan. Okay. There's visibility graph. So we are going to draw, basically create edges between all pairs of mutually visible vertices. So, we have these vertices, and we are going to create edges that connects these vertices. Then that gives you, pretty good starting point to create this roadmap, okay, edges. And it's going to be, pretty close to optimal roadmap, resulting optimal plan. But this is limited to straight motion, so we can only have straight motions between the vertices, and suitable for 2D and polygonal obstacles. Randomly sampled graphs. This has been a popular approach, especially popular for sample-based methods, which is going to be covered next lecture. Require careful consideration of construct graphs with some level of guarantees. Okay, we'll talk more about sampling-based methods. Planning with graphs. Given a representation, a start, a goal, and a motion model, how do we actually generate a plan? Many planning approaches use graphs because we know how to search graphs, and computers are good at it. Solve using an appropriate search algorithm. All right, so far we covered up to here. So we talked about representation, graph construction, and now we are going to talk about search algorithms, okay? Mainly Dijkstra and A* will be discussed in the following slides. And note that search algorithms can be applied to other methods as well. So search algorithm is it's search algorithm, but when we talk about graph sampling potential methods, it's grouped by more of how to create the roadmap, or what type of representation it uses, and how we generated the configuration space. So we classified these methods in that manner, but solver, the search algorithm, can be applied to different problems, different methods. Okay, so I'll talk. So let's introduce search algorithm here, and then we'll move on to other methods. Okay. Okay, let's continue with search algorithms. Search algorithms have, depending on conditions and the problem that you are facing, you need to select the right search algorithm, and we can group search algorithms into these three groups. First would be if you have uniform edge weights, then you could use breadth first search or depth first search. If you have non-uniform edge weights, then you should use either A* or Dijkstra. And there is more advanced theory and techniques called optimal control, including dynamic programming, model predictive control, variational methods. in this course, we are going to introduce you to this second methods. First is not very widely used these days. The second and third methods are widely used, but the third part is going to be a bit of too much information, or requires a lot of lecture materials and time to introduce you to those theories. So I will just stick to the second method, A star and Dijkstra's method, which is still widely used and practical and usable. Okay. Graph search problem. Edges can also have associated weights, cost of traversing the edge. We generally consider positive edge weights. A minimum cost path never revisits a node. Graph search methods are listed here. The first two is, as the name says, search method, literally, and you can see why from these search trees. First, we construct a tree through which we can search for optimal paths through the environment. So we're going to use this graph as an example for many of these search algorithms examples. Let's say you're starting from point A. Then you what search tree is you're going to create your action candidates as trees from starting from the A position. And as you can see, you can go either you have an option of B, C, and D, and that's what you're creating as a branch of a tree. And then you can branch out from those points to more options. So C, E, F, G, B, D, G, I, C, I, J, and we can continue with these combinations. The problem here is that the nice part is that we are considering all the combinations, all the paths, but then the problem is that this can be redundant, meaning that when we want to get to, let's say, a G, or let's say H, we want to get to H, but then there are many paths and many options to get to H, and each branch, and this continues, so each branch reaching to H requires computation, and that computation can be very heavy, because you are basically computing all the combinations, all the paths from A to H. So with that in mind, let's see how these search algorithms handle this tree search problem. So as I described in the prior slide, start the search tree problem is start state at the root node. Children correspond to successors. A node corresponds to a unique plan from start to that state. For most problems, we want to avoid building the whole tree. Use search algorithms to efficiently traverse a tree. So the key here is we want to avoid building the whole tree. And search algorithms to efficiently traverse a tree. So here's the Dijkstra's algorithm. This is published by Edgar Dijkstra in 1959. Basic idea of expanding in order of closest to start. One of the most commonly used routing algorithms in graph traversal problems. Asymptotically, the fastest known single source shortest path algorithm for arbitrary directed graphs. OpenQ is ordered according to currently known fast cost to arrive. So what this does is, just like we looked at the tree search problem, it's doing that here for robotic application or path planning problem. But the problem is that it's not that efficient. But let's first study what Dijkstra algorithm is first. So let's start with this example. So the starting point is going to be B, and then the edges, as you can see, the edges have cost to go, 5, 3, 2, they have cost to go. By the way, this is the pseudo code, and I'm going to basically explain what this pseudocode does. So we are going to build the tree, branch out the actions we can take, starting from B. So we can go to A, C, and G with cost of 5, 2, 3. So we have that cost written here, and then we can note the position and the total cost as shown here. Okay, then we have A5, C2, G3, and then we are going to continue branching out the path, and we can start from for each branch AC, each node, ACG nodes, we can do the branching. And wait, you can see that C can go to A, D, and G. It's not going to go back. So A, D, G are the options, and you're going to compute. So 2 plus 2, 2 plus 2, 2 plus 2 is 4, 4, 4, A4, D4, G4. But note that here we had A5, okay? And then here we had A4. So what's going to happen here is that we are going to remove this option, okay? So we no longer have to branch out this option, okay? And that saves some time, computation time, and memory. So here, we stopped here. and ADG. Oh, and then we note that we had this G3 here, but here is G4. So we don't need to keep this one, okay? So we're going to keep this one. So we now have I starting from C. So we have these three options, I4, D4, I7, and G3 is still alive, okay? And then we're going to continue to branch out starting from G3, which is going to be I8, which is not an optimal solution when compared to this one. So we can remove this branch, okay? We're going to continue. So starting from A, we have D, but that's worse than this one, 4. And then so we are going to stop here. And then let's continue with D. We have I, which is 5, which is better than this one. So we're going to remove that one. And then we can go to J. Which is the goal. So we're going to keep this one. And the path is this one, okay? Which is B, C, D, and J, which gives you total cost of 6, okay? So that's how Dijkstra works. At the end, we can recover the lowest cost route from the start to any node. We say any node because we kept these values. Quite easy to implement, but requires a little bit of careful management with the priority queue. Doesn't really know the goal exists until it reaches it. So the question is, could we guide the search to expand nodes that are closer to the goal earlier? Can we do it without breaking the condition that a node is only accepted with its lowest cost of arrival? So we're going to answer this in the next section, which is A-star algorithm. So Dijkstra had to simply solve all the possible path solution and finds the best path to the goal, but it was not that efficient, even though you could remove those path that is not worth computing by removing some of the branches when you compare them. But what A-star does differently is that here we can consider the position of the goal, or say cost to arrive, meaning that how much cost will it take from the current position to the goal. So if we know that value, then we can compute both cost to go and cost to arrive. Okay. So let me maybe I mix that terminology. So cost to arrive would be the cost to get to, let's say, this point. And then from here to there, this is going to be cost to go. Okay. Anyway, so by doing this, we can solve, we can find the solution much faster, much more efficiently. But the problem is we don't know the cost to go. Okay, meaning that how much cost it will take from this point to here. If we knew that, then we didn't have to solve this problem at all. So that's where approximation comes in for cost to go term using heuristic. So we can use any optimistic estimate of how close a state is to a goal designed for a particular search problem. Examples are Manhattan distance, Euclidean distance. If we use, these distance values, then we can approximately calculate the cost to get to the goal. But this doesn't always work nicely. Okay. First of all, if the edges are not uniform, it's highly likely that those links are not uniform, the cost. And then if there's an obstacle, then you might have to come around. So then this approximation is not that accurate. Okay. So anyway, the key idea is that if we can sum the cost to arrive and heuristic cost to go, then we can compute the entire cost from A to B, which is what we are interested in. We want to minimize F, but the problem is that we know this based on our computations, or cost to get to a certain point, but H is unknown, and we have to approximate that. And here is an example, A-star algorithm. So here in this example, we are going to start from B, just like the Dijkstra algorithm, and we want to get to J. But unlike Dijkstra, if you can construct this sort of heuristic cost to go map, where the distance is in this area, the H equals to 5. In this area, we're going to set H equal to 3. Here, H equals to 2. And in this region, H equals to 1, just based on distance. Okay, it may or may not be very accurate cost to go, but let's see how it works out. So we're going to start from B, the starting point. We're going to branch, create a tree just like the Dijkstra. A5, C2, G3. But then we are going to add the cost to go which was 5 for G, A for 5 for A, and then C would be 3. Okay, so we're going to add that value here, and then we're going to keep that value. So that would be 5, 8, and 10. And then 3. And then we're going to continue branch out. Starting from C, we can go to A, and then A is A4 plus 5, so which is better than this one. So we can remove that one. We're going to remove that one, and then let's try D. D has H equals to 2 for D, so that's going to be 6. And then G, we can move to G, which is here, and that's going to be 9, right? Where we already have this G3 plus 5, so that's better. So we don't need this anymore, and we can go with I position as well, and that's going to give you total of cost 8, and then we can branch out to A, which is worse than this one, so we can remove that one. But we can go to I, and we can compare that one with this path, which we can remove this one, and then we can go to J6, finally the goal. So as you can see, this is similar to Dijkstra, but it considers this cost to go. And what makes this different is that when we have this this path gives you cost of 8, which is large when compared to these options. So you're not going to branch these out. Okay, so that makes search algorithm a bit more efficient. Okay, so so that way you can find this path a bit faster, and the tree is sort of directed towards the goal, okay, by considering the cost go. But like I said, so and by the way, this does give you the same result as Dijkstra, right? This path was the solution we got from Dijkstra, and rough heuristic approximated cost to go map does help you with computation and memory when compared to Dijkstra, and still get the same answer. But if the heuristic cost to go map can still mislead and give you not the global optimal solution or path. Okay, in this example, it turns out to be the same. Okay, the heuristic must be admissible. It never overestimates the cost. H must be small or equal to cost to arrive. The heuristic must be consistent for any pair of adjacent nodes x and y, where dxy is the cost of the edge between them. Typical valid heuristics are Euclidean distance, Manhattan distance, and 0 for Dijkstra. Okay. A star is an extension of Dijkstra's algorithm and achieves faster performance by using heuristics. Best first search. A star traverses a graph following a path of the lowest expected total cost or distance. The cost function is sum of two functions, past path cost function, which is a known cost from the starting node to the current node, future path cost function, which is heuristic estimate of the distance from the current node to the goal. Limitations are you need to construct a graph for robotic application. Sometimes an admissible heuristic function is difficult to find. A grid may not be good representation of your problem. Okay. But it's still effective practical method for low dimensional state spaces. Okay. Let me go back to this slide. I'm not going to cover optimal control such as dynamic programming, but if you already learned dynamic programming, you probably can see some similarity between Dijkstra A star versus dynamic programming. What dynamic programming is basically doing is computing this for all combinations, but the main difference is that in dynamic programming you don't use heuristic cost to go. You actually compute that backwards in time or stage. Okay. So this concept, cost to arrive, cost to go, holds for many search algorithms and optimal control problems. Okay, so this will be it for this lecture, and I will see you guys on Wednesday. All right, bye-bye.